This is MAT5700 Lecture 42, and we will be covering 7.52 today, but I want to first remind you something about what we did in the previous subsection 7.51. So last time in 7.51, we recalled we did conditional probability for random variables x and y. So recall, if we have random variables x and y, we can define a a conditional probability mass function. This was the notation as this is the same as the probability that x equals x, given that y equals y. So x equals x is an event, so is y equals y. This is the usual probability of the events, and this is given by the joint probability mass function of x and y divided by the marginal one for y. Okay, so this is the discrete case, of course. And in the continuous case, it's given by, we have the, I don't need that. We have the corresponding density function. So this is given by f of x, y, that's the joint PDF over the marginal PDF. And this actually was defined way back when. And now what I want to talk about, what we did do was we did conditional expectation. So we do it like this: the expected value of x given that y is equal to y. Well, this is the same thing as the sum over all x's of the probability that x equals x conditioned to y equals y. In other words, it's the same as the sum of x over the sum over all x of the PMF. That's in the discrete case. And in the continuous case, it's actually given by, I'll do it in blue, the continuous case is given by the integral from minus infinity to plus infinity of x times f x y x y x conditioned to y dx. So that's in the continuous case. So notice this is for a given y, this is a number, but you should think of this as actually a function of y, of the variable y. So this is actually not a number. It's only a number when you plug in y. So this is really a function. In other words, it's a random variable. So that's what it's a random variable. Okay, so let me give you two examples of this. One will be a discrete case, and the other will be a continuous case. Okay, so the first example is to roll a fair die until you keep rolling until 6 appears. So let's let y be the number of rolls you make. So that could be anything, 1 or 2 or 3, all the way up to 1,000,000. You might not get a 6, right? Then x will be the random variable, the number of ones number of times one appears in all your rolls. And then I want to compute the probability, the conditional expectation of x given that y equals y. Okay, so let's think about what this means. So I want to grapple with it. Okay, so what is y equals y? This is an event. What does it mean? It means you rolled y times until you got a 6. So this means it means y minus 1 rolls. You didn't get a 6. No 6 appeared. And then the yth roll, you get 6. That's what y equals y means. So and now what is x here? X is the number of times one appears in the y rolls if you're conditioning it to y equals y. So x given, let me say it this way, given that y equals y, x is Bernoulli, a Bernoulli random variable of type y minus 1, because we're trying to compute the number of times 1 appears, and 1 must appear in the number of times 1 appears are in the y minus 1 rolls, because the last roll is a 6, and then the probability of getting 1 in any of those y minus 1 rolls, the probability of getting 1, since you know that you're not going to get a 6 in any of those rolls, that can't happen in this case in the conditioning, is 1/5, because there are 1 out of 5 possibilities. You either get a 1, 2, 3, 4, or 5 when you roll the die. So x is a binomial of type y minus 1 1/5. So we can give under this conditioning rule, given that y equals y. So therefore, the expected value of x given that y equals y is, here n is y minus 1 and p in the binomial is 1/5. So it's n times p, which is 1/5 times y minus 1. In other words, y minus 1 over 5. So that's an example. That's our example. You get y minus 1 over 5. Okay. So what I want to do now is a continuous example. So here's our second example. Let's consider the joint distribution, the joint density, e to the minus x over y times e to the minus y over y, where x is varying from 0 to infinity and y is varying from 0 to infinity. So you're in the first quadrant. And let's find the expected value of x given that y is equal to some number y. Okay, so let's compute this. How do I compute? The first step, step 1, is let's compute the conditional density function. So, which was, recall, f of xy, the joint density function over the marginal density function. So now in order to do that, we know what the numerator is that's given to us up on top. It's just the denominator we have to compute. So what is f sub y of y? Well, that's the integral from minus infinity to infinity of f of x y dx, which is the same thing as the integral from 0 to infinity. Since we're in the first quadrant, x and y are only non-negative, integral from 0 to infinity of the joint density. Well, and this is dx. So we can bring, if we compute the antiderivative of this integrand, you'll see that you'll get e to the minus e to the minus y times e to the minus x over y, because its x derivative is precisely the integrand. And we're going to evaluate it from x equals 0 to x equals infinity. And if we do that, what do we get? Well, you see easily that when we plug in x equals infinity, it vanishes. We plug in x equals 0, we get e to minus e to the minus y. So it's going to be e to the minus y is the marginal density function for y. Okay, so this tells us what the conditional density function is. It's given by the numerator, which is e to the minus x over y times e to the minus y divided by y. That's all the way on top of the screen, on top of the slide. And then we're going to have to divide by e to the minus y. What do you get? You get e to the minus x over y divided by y. Okay, so that was step one. Step one. This was the end of step one. Now we have to compute step two. So step two is to actually calculate what is being asked, the expectation of x given y equals the random variable y equals y. So that's going to be the integral from minus infinity to infinity of x times f, the conditional density, and we integrate it with respect to x. And what do we get? Well, if you do that, that's going to be the integral from 0 to infinity of x. We just computed this conditional f, right? It's going to be going from 0 to infinity now, and then we have to plug in what we got in the previous step. And then we integrate with respect to x. And again, this is fairly easy to integrate. This is going to be given by minus x e to the minus x over y, because the x derivative is precisely the integrand, and it's going from x equals 0 to x equals infinity. And I didn't do that correctly. Let me back up. I made a mistake. That's wrong. I have to compute this integral. Now, this is a dx integral. It's an x times e to the minus xy. So you can do this by parts. We can do an integration by parts. Let me pull over here, integration by parts. So we're going to let u equal x, and then du is equal to dx. dv is what's remaining, which is e to the minus x over y divided by y. So v is minus e to the minus x over y. So if we do that, we get the integration by parts. It becomes minus ex e to the minus x over y from x equals 0 to x equals infinity, plus the integral from 0 to infinity of v du, which is e to the minus x over y dx. Okay, so you can evaluate this. What ends up happening is that the first term just goes away. There's nothing there. And the second term integrates out to, it ends up being y. That's an easy calculation, which I won't do. So we've just computed the conditional expectation. Notice that this is not a number. It depends upon y, so it's a random variable. So we've just computed a random variable. Okay, so now we get into subsection 7.52 proper. So we saw in the previous section that e x y equals y depends on y. So it depends on y. It's a number depending upon y. So you can think of EXY is a random variable whose value well, so it's a random variable. Okay, so what I want to do is I want to define it as, so what I want to do is I want to compute its expectation. What is the expectation? That's what the content of this section is. So it turns out that there's an answer. The expected value of this random variable just gives you the expected value of x. Okay, so what I'm going to do is I'm going to give you a proof in the continuous case, but first, before I do that, I want to tell you what the formula says in the discrete case. In the discrete case, this means that the expected value of x can be broken up as a sum over y of the expected value of x given that y equals y times the probability that y equals y. In other words, it's the sum over y of the expected value x conditional to y equals y of p of y. So that's what the formula is saying there. I'm going to give you a proof of this formula, though. This is the formula in the continuous case. Okay, let me do that. Okay, so what is the proof? So so what is by definition, what is this going to be? Well, if you remember, this is by definition, if you have any function, its expectation is given by that function integrated against the density. So this is going to be the expected value of E xy times f sub y of y dy, because this is a function of y. And this thing inside, E x dash y, is a function of y. It's a random variable in y. Okay, so now what is this? So this is given by the integral from minus infinity to infinity. Let's plug in what this expected value is. This is the integral from minus infinity to infinity of f x times the marginal PDF, give f sub x of xy dx. So that's what it is, and then we have to multiply this by f sub y dy, and so that's what it is. Okay, so now we have to rewrite this somehow. Okay, and one way to rewrite this, and I want to bring the dx out. This becomes the integral from minus infinity to infinity, minus infinity to infinity. If we multiply this with this, what do we get? We get the joint density function. So by the way, I'm not using correct notation here. Let me erase this and make the correct notation. This should be f sub x of x. Yes. Okay, so did I do this right? I'm confused. Hold on. Yeah, what goes here is if you go to the beginning of today, it's given by the expression, the conditional density here. Okay, so what I'm going to do is I'm just going to reorder the terms now. This becomes the same thing as, but let's remember that this expression is given by the joint density divided by the marginal density in y. So when we multiply these two terms together that I'm going to connect up, I get x times f of xy appearing, and then there's a dx, and then there's a dy. Now, if we do that, and we rewrite the integral in this way, we'll bring the x out, and we integrate away the y variable first. I'm doing a Fubini theorem. What do we get? What we get here, this expression in the parentheses, is by definition f sub y of y. I'm sorry, f sub x of x. So let me erase that. It's f sub x of x. And the integral of f sub x of x times x, that's the definition of the expected value of x. And that's what we had to show, right? That's what we had to show. We had to show this was equal to this, and we did. Okay. If you didn't understand that proof, that's okay, but I wanted to show it to you. So as an illustration of these ideas in the discrete case, let's consider example 5C in this section, which is about a trapped miner. So there's a miner that's trapped underground, and the miner has to has three choices. There are three tunnels. So there's tunnel 1, tunnel 2, and there's tunnel 3. And in tunnel 1, the miner doesn't know which tunnel is which. This tunnel leads you out. This leads you out, leads to safety, and it takes 3 hours. Tunnel 2 returns back to where you are in 5 hours. So this is not a good tunnel. Tunnel 3 is not a good tunnel either. It's even worse. You return in 7 hours. Okay, so now the miner is stuck in the tunnel, completely confused, and chooses one of these tunnels randomly. So let's let the probability of choosing a tunnel is 1/3. Each one of the tunnels, so it's equally likely. So we want to compute the expected value, find the expected value of what it takes of the time to get to safety. So let's define some random variables here. So let x be the expected time it takes to get to safety. Let y be the choice of tunnel, the initial choice of tunnel. Okay, So now we're going to use this formula that we just derived in the continuous case, but the discrete case is the same statement. So this would be, if you write down the formula, this would be the expected value of x given that y is 1 times the probability that y is 1 plus the expected value that x given y is 2, second tunnel, times the probability that y equals 2 plus the expected value of x given y is 3 times the probability of 3. So we know what the probability of 1, that y equals 1. That's the same as the probability that y equals 2, which is the same as the probability that y equals 3, which is all a third. That's given to us. That's given. So we have to compute the other terms of the expression in order to get the answer to the problem. So what is the expected value of x given that y is value 1? Well, that we know that. That's easy. If he chooses the first tunnel, the miner, the expected value of returning to safety is 3 hours. That's easy. But now the other two cases are the expected value of x given that he chooses tunnel 2 initially. So what happens? He takes tunnel 2, and then that takes him 5 hours. Then he's back to where he started. And then back to where he started, there's an expected value of getting to safety, which is the expected value of x again. So that's easy enough. And similarly, if he had chosen the third tunnel to leave by, he would go through the tunnel 7 hours, come back to where he started, and then you would add to that the expected value of leaving the tunnel to safety. Okay, so we now have the following equation. So we get that on the left side, if you remember, we had on the previous slide, we had E of x equals the expected value of x given that y equals 1 times the probability of y equals 1, which we know to be a third, plus the expected value of x given that y equals 2 times a third, because that's choosing tunnel 2, plus the expected value of x given y equals 3 times 1/3. And now we know what these things are, more or less. The first thing we got was 3 times 1/3 plus 5 plus e of x times 1/3 plus 7 plus e of x times 1/3. So what do you get? You're going to get we have to expand this out. We get 1 plus 5/3 plus 7/3 plus 2/3 e of x. I'm just expanding out the right side is e of x. In other words, 1/3 e of x equals 1 plus 5/3 plus 7/3. So that's 12/3, which is 4, which is 5. And therefore e of x was 15 hours. So that's the answer to this example. So the expected time is 15 hours. Not too good. Okay, well, that's it for today, subsection 7.5.2. We will continue next time.